Welcome back. We were analyzing a modulated signal in frequency domain in the previous lecture. Today we will start our discussion by analyzing the signal in time domain. Let's stick to the arbitrary message signal we were using in the previous lecture. The shape of MT was like this. There is an interesting fact about this particular message signal. That is, it has the same maximum value in both positive and negative side. That is MP. Also, this signal is fluctuating across the zero voltage line. In practical scenarios, you may encounter message signals of any shape. We were using a carrier signal AC cos omega ct. The equation of the modulated signal was AC plus MT multiplied by cos omega ct. We will try to draw the modulated signal here. Let's consider some values. Let's say MP is equal to 5 volt and the carrier amplitude AC is equal to 10 volts. When we will add AC and MT, actually an offset of 10 volt will be added to the message. That means the zero voltage line will now be shifted upwards by 10 volt. And this point in the message signal, which is 5 volt, will now be 5 plus 10 equal to 15 volts. And this point in the message, which was minus 5 volt, will now be minus 5 plus 10 equal to 5 volts. This AC plus MT signal is known as the envelope ET. Now think about a sine or cosine wave. The property of a cos wave is it varies between the positive and negative values of its amplitude with a certain frequency. We have already got the amplitude of the modulated signal AC plus MT. Now we will need to draw the reflection of it, which is denoted by the dashed line. This is actually minus of modulus of AC plus MT. Then we will need to draw a cos wave with omega c frequency in between. However, this is not the case always. Consider this same example with the same message signal, except now AC is equal to 3 volts. Now this zero voltage line will be shifted upwards by 3 volts, and this point here, which is 5 volt in the message, will now be 5 plus 3 equal 8 volts, and this point here, which is minus 5 volt, will now be minus 5 plus 3 equal to minus 2 volts. Similarly, we will draw the reflection of it and insert the cos wave in between. So whatever the values and shapes of AC and MT are, the process of drawing modulated signal is the same. We will follow 3 steps. Step 1. Add AC and MT and draw the envelope signal. Of course, the shape of the message will be unchanged, just it will be shifted up by AC. Step 2. Draw the reflection of the envelope signal considering the 0 volt line as mirror. Step 3. Finally insert the cos wave in between. One last thing to mention here. When you will transmit this signal and the receiver will try to regenerate the message, one way of this is envelope detection, where the envelope on the positive side is considered as the shape of the message. This is true. As you can see in the left, the envelope of the positive side is actually the shape of the message. However, on the right, this is not true. The envelope here is not the true image of the message. This happens when some part of AC plus MT is less than 0. So we can use envelope detection when AC plus MT is greater than 0 for all time. We will be introduced to a new concept here, that is modulation index mu. As you can see from this equation, mu is equal to the ratio of Emax minus Emin and Emax plus Emin. I have already told ET is the envelope signal, which is AC plus MT. So Emax is the maximum value of AC plus MT, but as AC is a constant term, so Emax can also be written as AC plus MT max, or AC plus the maximum value of MT. Similarly, Emin is the minimum value of AC plus MT, or in other words, AC plus MT min. Two different scenarios can occur here. First one is the case for the signal we were using as the message, or any sinusoidal signal, where maximum value of MT, which is MT max, and minimum value of MT, which is MT min, have same numerical values, even though their sign were different. So in that case, MT max is equal to minus MT min is equal to MP. So Emax will be AC plus MP and Emin will be AC minus MP. If you put the values of Emax and Emin in the equation of mu, you will get mu is equal to mp by AC. Another case is where mt max is not equal to minus mt min. You can carry out the calculation using Emax equal to AC plus mt max and Emin equal to AC minus mt min and reach this conclusion. But practically this is a very rare case and we will not consider this case further in our course. So we will continue using mu equal to mp by AC, where mp is the peak value of the message and AC is the carrier amplitude. We have already talked about envelope detection. It required AC plus mt to be greater than or equal to 0 all the time. We can also say if AC plus mt min is greater than or equal to 0, then AC plus mt will always be greater than or equal to 0. Now for case 1, mt min is minus mp. So AC minus mp must be greater than or equal to 0. If you rearrange it a bit, you will get mp by AC less than or equal to 1, which means mu need to be less than or equal to 1. Again, mu is a ratio of two positive quantities, so mu must be greater than or equal to 0. So this is the condition for envelope detection. If mu is less than 1, it is called under modulation. If mu is equal to 1, it is called 100% modulation. And if mu is greater than 1, it is called over modulation. Envelope detection is not possible for over modulation. We will talk about single tone modulation now. Single tone modulation means where the message is a cos or sine wave of a particular frequency. In this case, the message is am cos omega mt. The amplitude of the message is am and the frequency is omega m. One thing to mention here is omega c is very much greater than omega m as we modulate low frequency message with high frequency carrier. As usual, the modulated signal will be AC plus mt cos omega ct. In this case, mt is equal to am cos omega mt. If AC is taken common from both sides, the equation will look like this. Of course, the mu pops up here because mu is equal to am by AC. Another way of analyzing this signal is shown here. The first part is the carrier itself and the next part is the modulated carrier. We can further use the formula of 2 cos A cos B to reach this conclusion. From this equation, we can draw the spectrum of the modulated signal. I would encourage you to practice drawing spectrums like this using arbitrary values for AC, AM, omega C and omega m. I have already shown how to draw modulated signals in time domain too. Hopefully, you will use that knowledge to make some sense out of these figures. Let me recap the frequency spectrum of the message and the modulated signal here once more. So this is the spectrum of a message. It has symmetry components in both positive and negative frequencies. The portion in the positive side is called the upper sideband or USB and the portion in the negative side is called lower sideband or LSB. Obviously, they are just mirror image of each other. When we modulated this signal with high frequency carrier, this whole spectrum was shifted to omega c center frequency and minus omega c center frequency. And the amplitude of each of these two parts are half of the original amplitude. In the negative part, the USB and LSB gets flipped. You will get to know the reason if you take the Fourier transform of the modulated signal. Back to our discussion. The modulated signal has two parts, as I have already said, the carrier itself and the modulated carrier. The power of a cos wave is half of the square of its amplitude. So the carrier power in this case is half of AC square. On the other hand, the power of the modulated carrier is called the sideband power and it depends on the message signal. In the modulated AM signal, only useful power is the sideband power as we are concerned with message only and not the carrier. So the efficiency is useful power by total power, which is PS by PC plus PS. In the case of single-tone modulation, we have derived this equation and the only difference is previously this value was AM and now it is mu into AC. These two are basically equal because mu equal to AM by AC. So we have two cos waves in the sideband here. The first one corresponds to the USB and the second one corresponds to the LSB. Both of these cos waves have an amplitude of mu into AC by 2. So the power of each cos wave or the USB power and LSB power both will be mu square AC square by 8. So total sideband power, which is USB power plus LSB power, is mu square AC square by 4. Now we can calculate the efficiency of the DSBC AM. The efficiency will be mu square by 2 plus mu square. This is a very easy calculation if you put the values of PS and PC in this equation. Now, if mu is 0, the efficiency is 0. If mu is 1, the efficiency is 1 by 3. So the maximum efficiency we can achieve here is just 33%, which is not very efficient. Let's talk about the multitone modulation. In the case of multitone modulation, the message signal contains of multiple frequency components. Here you can see the message is a sum of n cause waves which have different frequencies such as omega 1, omega 2, omega 3 up to omega n, and they have amplitudes of A1, A2, A3 up to AN. If you put this MT in the equation of modulated signal, you will get this equation. If AC is taken common, then we will get this. Here, mu1 equal to A1 by AC, mu2 equal to A2 by AC, mu3 equal to A3 by AC, up to mu n, where mu n is AN by AC. If you compare this with the single tone, you will observe a similarity. Previously, there was only one component, and here are n components instead. For single tone modulation, the sideband power was mu square AC square by 4. But now, as there are n components, PS will be sum of all the mu squares multiplied by AC square by 4. We can rewrite this equation as mu T square AC square by 4. Now we have generalized the equation of total sideband power for multitone. So total power PT will be PS plus PC will result into this 1 plus mu T square by 2 into PC. Mu T is called overall modulation index. One thing to note, this overall modulation index mu T may not be equal to the normal modulation index mu. In mathematical problems, when you will calculate efficiency for multitone modulation, the formula is same as the single tone. Efficiency will be equal to mu T square by 2 plus mu T square. We have learned that mu must be less than 1 for ensuring envelope detection. But as mu and mu T are different, if mu T is less than 1, it does not ensure envelope detection. That's all for this lecture. See you on the next.